discussing the fundamentals of multi-component systems, and in the last class we talked about partial molar properties, and I had given the definition. We had seen that this was from the basic equation we were able to get the definition for partial molar properties as the gradient of any extensive property with respect to the number of moles. And I had asked you how should we determine it experimentally. We had also seen a physical interpretation of it. What was the physical interpretation? That itself should give you a hint at which the manner in which experimentation should be done, say for a binary mixture, to find it out. The physical interpretation which we had also seen last time was, it is the rate at which the property of the entire multi-component substance would change,
changing the
number of moles of that particular component. Conditions are temperature is maintained constant and extent of all other components remain fixed. Now, this very interpretation should give you an idea how you have to do an experiment. As I had said last time also, suppose you want to do measurement of aqua ammonia mixture, find out its partial molar volume with respect to say water. Okay, what will you do? How will you do the experiments? If you understand this, then you should be able to tell me how the experiment should be done to find out the partial molar volume.
So we will change the volume of one component and we will find out the effect on the total entire system.
So if you have to do it for water ammonia mixture and find out the partial molar volume with respect to water, what will you do? At a certain temperature and pressure, you will mix ammonia and water in certain amount, certain proportion. Now at that composition, if you want to find the effect of, you find the partial molar volume for water, you will add a small amount of water to it, keeping temperature pressure constant. You will add small amount of water and find out how much is the increase in the total volume, isn't it? So the ratio of increase in the total volume to the number of moles added will give you del V by del N, if you take the limit and delta N tends to 0, that will be the gradient, isn't it? So what experimentally what you can do, at various number of moles, keeping various compositions, at certain number of moles you add small amount of water, find out what is the increase. Or what you could do is, you could take number of compositions, keeping the number of moles of ammonia constant, you find out what is the volume at one number of mole of water, that another number of moles of water, then another number of moles of water, and then plot that graph, and from that graph you can get the value of partial molar volume, is it? So how will you get the experimentally determine it? You will have to do experiments in this case type and say eventually plot the property M as a function of Ni. It could be volume, it could be enthalpy, entropy, whatever. Of course, volume can be easily measured. You can't measure entropy. There you will have problems. You will have to think what can be measured and what cannot be measured. So you can find out what is the value of that particular property as a function of number of moles of that particular component. And if you draw this curve, and then at any point, at any composition, if you draw this tangent, the slope will be equal to Mi bar. Clearly, the slope will vary from each value of Ni. So Mi bar is not a constant. It is a function of Ni also. It is in fact a function of everything else. Just as M is a function of T, P, N1, N2, Ni, in fact Mi bar will also be a function of T, P, N1, N2, N3 and so on, because it is obtained by partial derivative of that. Okay. So this is how you could visualize experimental determination. Of course, you can see if you do like this, you will have to do huge amount of experimentation. Even for a binary mixture, you will have to do so many experiments, keeping a number of moles of ammonia fixed, then you do large experiment, then you change the number of moles of ammonia, then do again experiments, and similarly keep on doing. You can have a better method, which we will discuss later, where you do not have to do such a large number of experiments. That will come later. But the physically one should have a picture, how do we really visualize partial molar volume as. Had suppose there had been no interaction between ammonia and water, what would have happened? What would be the partial molar volume? How much? How much will it be?
It will be by the amount of by which we are adding.
So how much will it be? You are adding water, so it will be the increase in the volume will be increase in the volume of the water divided by number of moles of water. So it become equal to specific volume of water itself, isn't it? If you have no interaction between molecules, then the partial mole volume will be equal to the corresponding specific mole volume. Intuitively it is clear, and this will apply to any other substance, not just to liquids or gases, but to solids also. We apply the same theory in metallurgy. You have formation of alloys, solid solutions, also the same basic theory will apply there also. You can also get a physical interpretation if you look at the basic equation once again. Of course, we spoke about it earlier, but let me see. From this equation, what idea do you get of mi bar? This was the basic equation which we had said, defining the extensive property m as a function of number of moles of component I. Now, from this equation, what does it convey? What is mi bar? You compare it with the equation which we had got in the absence of interaction. If we had each of the species, each of the components separately and not interacting with each other, then m would have been Ni into Mi0. You remember?
Yeah.
The corresponding property of that species,
Pure substance.
isn't it, of that component. Now, here we are having Mi bar. So, what would you say partial molar property therefore is? What can we visualize this as?
It is similar as property of pure substance.
It is some pseudo property, isn't it? It is some kind of a property of, we say, species I, as it is actually existing in the multi-component system. Not it actually is when it is pure. So, we say it is molar property of species I as it exists in the multi-component system. Of course, in reality component I does not exist separately, it is all intertwined. There is a molecular interaction, and in fact the interaction is so strong that you can't really identify, even in air, this is nitrogen molecule here and this is oxygen and they are separate. You can't do that, they are so strongly interacting with each other. So, it is not that you can really have each component having its own private property, that is not true, isn't it. So, in reality the constituents of a multi-component system are intimately intermixed, and therefore you cannot assign, you cannot say these have individual properties of their own, but it is some sort of a mathematically assigned property for the sake of convenience, you can say. So, mi bar should therefore be interpreted as an assigned property value in view of the earlier equation. Okay. So, these are the kind of physical interpretations which you can give of the partial molar property. Okay. Now, this relationship which we obtained between partial molar properties and the total property, we obtained by some invoking the property of a extensive property. No, what is the property of the extensive property? Have a relationship that the extensive property is such that the value of extensive property for two systems is equal to the extensive property for the double of that for individual. Now, that kind of a argument can be extended to any extended property, any extensive property, but there is a general mathematical theorem which, if you use, it gives you a more elegant way of looking at it, and then you can easily apply it to the other properties also, because otherwise you will have to apply it every time to do the same kind of mathematical ploy in finding out the relationships. So, rather than do that approach which we did in the last lecture, we will derive here today very simple, what is called Euler's theorem on homogeneous functions. I do not know whether you have studied it in your mathematics class. Have you?
Yes, sir.
You studied? What is that? Tell me.
For a homogeneous function, I can't remember. I have studied in BTech, so I can't remember the exact form for homogeneous function.
What is a homogeneous function?
Which can be expressed in the form of y by x.
No. What is a homogeneous function? Anybody?
Means there is at least one term of the independent variable.
One by one.
Equation in which there is at least one term of the independent variable.
All terms are of the same degree.
Yes. What does it mean? You are right, but you should put it mathematically. Not necessarily linear, no. This is a nearest answer which he has given, but the definition, mathematical definition is
This term
that if there is a function of z1, z2, zr, we say that it is a homogeneous function of degree m in zi, provided if you multiply each z by a certain number, the result will be multiplied by the same number raised to the power something. Okay. So, we say then if this equation is true, if you multiply z1, z2, zr by lambda, the final result is multiplied by lambda raised to the power m, where lambda is any constant. So, we say this is a homogeneous function of degree m. Algebraically, you could say it will have the order of each component, as you said, degree of each component. So, you could have, say, homogeneous function of x1, x2 would be a x1, x2 plus b x1 square plus c x2 square. This will be a homogeneous function. Why? Because if you multiply x1 by a certain fixed number, x2 by a fixed number, the result will be multiplied by raised to the 2, that number raised to the power 2. Okay. So, we say this is general definition of a homogeneous function. And what is the Euler's theorem? That for such a function, you can say that the gradients, if you multiply them by the function, they will give you the original function. M into f function will be equal to zi into df by dzi. On one side you have the function, on the other side you have the gradient multiplied by the dependent variables. Seems very interesting result. Very simple to prove. How? It takes 1 minute. We define, say, new variables gamma 1, gamma 2, gamma 3 like this, where we multiply each of z's by lambda, which is the constant. So, we define new values of gammas, and then we can say this, when you multiply this by lambda, each of them, we had said definition of homogeneous function was f lambda z1 z2 is lambda m1, isn't it? So, we can now defining gamma 1 like this, we will say that for an homogeneous function, therefore, f gamma 1 gamma 2 should be equal to lambda m into f z1 z2 z gamma. This is the definition of homogeneous function. Now, if this is the definition, we can differentiate this with respect to gamma, keeping lambda constant, keeping zi z2 constant. What do we get? If we differentiate with respect to gamma, or differentiate with respect to lambda, differentiated with respect to lambda, not gamma. So, if you differentiate with respect to lambda at constant values, now gamma is a function of lambda into z1, gamma 2 is a function of lambda into z2. So, gamma 1, gamma 2 all are functions of lambda. So, you will write df by d gamma into d gamma by d lambda. And what will be d gamma by d lambda? Any gamma differentiated with respect to lambda will be how much?
Z.
It will be the corresponding z. So, you will straight away get this result. This is with respect to gamma, I think with respect to lambda is strongly written. Let me correct it here. Okay. So, if you differentiate with respect to lambda, this will be the result, because when you differentiate with respect to lambda, lambda m will give you m lambda m minus 1, all this is constant. Here when you differentiate with respect to lambda, because gammas are all functions of lambda, you will write differentiation with respect to gamma 1 into d gamma over d lambda, and each of d gamma over d lambda will be zi. So, you get this result. Okay. And what will be the, this is the general result which you get. Pardon? Yeah. So, this is del f by del gamma, this is d gamma by d lambda. So, this total is df by d lambda. Okay. So, this is the general result which you get. This is valid for all values of lambda. Now, you put lambda equal to 1 and you will get the result. You put lambda equal to 1 in this equation, because it is valid for all lambda, you will get the Euler's theorem. Okay. So, very simple, very interesting result. Now, why should we be interested in this? Can you tell me why are we interested in Euler's theorem suddenly?
Partial.
Hmm?
We have different components, and we are
Find the
changing that
partial
one molecule separate component,
Hmm.
and we are finally seeing that what is the total change in the final for the final component.
So, mathematically what does it mean?
So we are dealing with the partial change of different components and a total function.
No, you are not hitting on the nail. What is the final, why are we talking about it? Homogeneous function.
We want to find out the change in the
Total system. Did you change
extensive
that?
property.
We want to do it because an extensive property also is an homogeneous function. That is the simple thing. Why is it an homogeneous function? Because what is the definition of extensive property? This is the mathematical definition of extensive property. If you change the number of moles of each component by lambda, the final property is multiplied by lambda, keeping temperature and pressure constant, isn't it? If you have one multi-component system here, another multi-component system here, the total property of the composite system will be double of their each component, which means number of moles of each is multiplied by 2, overall property is multiplied by 2. So, this is the mathematical definition, isn't it? If you multiply number of moles of N1, N2 by lambda, the value of this property is multiplied by lambda, keeping temperature and pressure constant. Temperature, pressure are anyway intensive properties. That is another interesting thing to be noted. T and P are intensive properties, otherwise you will have problems. So, what does it say? M is a homogeneous function of degree. What is the degree?
One day.
Degree 1, because it was lambda raised to power m, we had said. We had said a homogeneous function, this was the definition of homogeneous function also. You multiply each by lambda, you get lambda raised to power m into the value for 1. So, you can see m is a homogeneous function of degree 1 in ni's. Okay. And if this be the case, if you understand that, then you directly write down the final result, which we derived by some manipulation in the earlier case. What will be the Euler's theorem therefore? What will be the Euler's theorem result? Apply that, write down the Euler's theorem for m when it is a homogeneous function of degree 1. Write down. It is very simple, you just change the notation only. Instead of function f, we have function m. So, what is the Euler's theorem?
Del m by del gamma.
M into f is equal to zi df by dz. So, instead of f, we have m, and instead of the raised to power m, degree m is 1 here. So, you get m will be equal to ni dm by dni. That was the result which we wanted to get, which we got by a complicated method in the earlier case. What will be an intensive property? Suppose m was an intensive property, could we define it also as homogeneous function or not? No?
Homogeneous of degree 0.
Homogeneous of degree 0, good. So, what will be the result? For a homogeneous function of degree 0, what will be the result? You will not be in a position to direct you to get it, but what will be finally result would be that the property would be the same. Okay, there is no change. Now, this general theorem, if you can apply now to each property, and one of the important results which we get is when you apply this to Gibbs function. So, apply this to Gibbs function, let m be the Gibbs function and see what you get. Instead of m, you will have g, and then have a look at that partial derivative. So, let me write down directly. When you apply to Gibbs function, you get g will be ni dg by dni tp nj. And can you identify what this partial derivative is?
Mu
Mu I.
It will be the chemical potential. You see the earlier we had given mu I in terms of 4 different derivatives, isn't it? So, at constant temperature and pressure, from the fundamental relation we have already in fact got this fact that this gradient is equal to mu I. So, we get a one step direction towards understanding what this mu I is. You put it together here, you will get the result G will be summation of Ni mu I. So, chemical potential is directly related to the Gibbs function. So, you are coming closer to the other thermodynamic properties now. Okay. Suppose we apply this to pure substance, what will you get? Because that is the way of understanding at least what this chemical potential is. For a pure substance, what will it be? How will this relation become?
G is equal to
Mu into N, total number of moles. And therefore, for a pure substance you will say capital G will be mu into N, or mu will be G by N, which is the molar Gibbs function. So, for a pure substance the chemical potential equal to molar Gibbs function. So, you have an idea now, okay, for a pure substance that is the value. For a multi-component system it is some kind of a pseudo Gibbs function which is trying to give us the value of Gibbs function contribution in the overall multi-component system. How much is the contribution of component I in the overall Gibbs function is given by chemical potential of that substance. Clear? Now, multi-component system thermodynamics is famous, or we may say infamous, for large number of relationships, interrelationships, because you have so many properties, new properties introduced. So, I will therefore present to you only a few of them. Okay. The people who study the multi-component systems in great detail are the chemical engineers, where we have to really study these in enormous detail. From mechanical engineering perspective, we have the requirement of studying multi-component systems from the point of view of partly from refrigeration, air conditioning, partly from the the combustion processes which happen, chemical reactions which happen. But even in them we do require certain basic minimal relationships between properties. So, we study a few of those relationships between various thermodynamic properties which are involved in multi-component systems, and one such very important relationship we call as the Gibbs Duhem equation. We will get it in a general form and then you can apply it to any property. So, we start firstly from the basic definition of the partial molar property. What was that definition? Property M is equal to Ni Mi bar. Okay. So, from that definition you differentiate and find out what is dm. What will be dm? This should be Mi bar. So, kindly read it as Mi bar. How did we define the any property M? We had said is equal to number of moles Ni into Mi bar. So, what will be dm then? Change in the total property will be due to change in Mi bar and change in number of moles. So, you can write down therefore that dm will be equal to Ni dmi bar plus Mi bar dni. Okay. This should be clear. This is the general relationship for change in number of in the any extensive property M, which accounts for the change due to change in the partial molar property and change in number of moles. That is one way of defining. Other could be look at the complete dependence of M. What is the complete dependence of M is on temperature, pressure, number of moles. So, you could also write down M as a function of Tp N1 and 2, isn't it? So, from this what will you get as expression for dm? Can you write down the complete expression for change in value of property? It could change due to change in temperature, change in pressure, change in number of moles. So, you can write down all the components. So, please write them down. Write down the expression for dm. What will it be?
del m by del t into dt,
Hmm.
keeping p and n constant.
Good.
Then del m by del p into del p, keeping t and n constant.
Good.
And the sigma of del m by del n when I is not equals to j, keeping p and p, t and n this constant.
And what is that? What is that gradient?
That will be the
Third gradient. Del m by del n I, keeping t, p and j constant. What is that called? We have defined it.
mu.
M is general property. It is the partial molar property. Definition of partial molar property. So you can write down therefore dm is equal to dm by dp, dm by dt into dt plus dm by dni because into dni, and this mi bar is of course the partial molar property. You can see this is the complete expansion dm by dni tp nj, which is mi bar. So you got two expressions for dm, one is here in terms of partial molar property change, other in terms of changes in p, t and number of moles. So the two should be equal. So if you put them equal, you can cancel out some things and get an interrelationship between changes in temperature, pressure and partial molar property. So find it out. How much do you get? What do you get?
We get the del m by del p into t into n, t and n constant.
This equal to this one. This will cancel out.
Yes.
Mi bar dni bar will cancel out, and you get from these two equations this mathematical result we get, which is called the Gibbs Duhem equation. What is the physical importance of this equation? What is it giving us?
That
For any multi-component system, it will tell you that if there is a change in pressure, change in temperature,
and change in the molar,
how will it be related to
change in molar speed.
change in the partial molar property. Again, the most important case of this Gibbs Duhem equation arises when m is equal to the Gibbs function. That is the special case. So write down what will be there. If m is Gibbs function, what will this equation become? Please write down. You can say dg by dp, dg by dt and ni bar dmi bar. Mi will be dgi bar. Then find out what are these each of these gradients, because you know already what is dg by dp t n constant, what is dg by dt when p and n are constant, and what is gi bar, that also we know. So put it down in terms of various other properties. Refer to the expression which we had written down for the fundamental relation for dg. Have a look at that, and then from there find out what is dg by dp when t and n are constant.
That is equals to v. That is equals to v.
That is v, and similarly what is dg by dt?
That is equals to
Minus s. Good. And what is gi bar?
that will be
Gi bar is the
mu.
chemical potential, isn't it? So you get a very interesting result, one of the most important results which is often used, special case for m equal to g, which quite often you will find in books the Gibbs Duhem equation is written as only this equation, which will become v dp minus s dt minus ni d mu I equal to 0. So you can see this importance of this equation. It is going to tell us the relationship between change in pressure, change in temperature and change in chemical potential of a multi-component system. Clear? If we further have the case and temperature and pressure are also maintained constant, as I said, in many chemical processes are done under constant temperature and pressure, what will happen? This equation become
Sigma Ni d mu I
Sigma
is equal to 0.
Ni d mu I is 0, or for the general case you will have sigma Ni dmi bar equal to 0. Even for the general case you will get this result. Again, important result. But when a chemical process is taking place, when any multi-component system, a process is occurring at constant temperature and pressure, then the changes in the partial molar properties are related to each other. They are not independent of each other. So, if you have a binary mixture, change in the partial molar property of one will be related to change in the partial molar property of other. Or if you want to put it in terms of chemical potential, if you know the chemical potential of one component, you can find the chemical potential of other component. Okay. So, that is the advantage of this kind of a relationship. Is it clear? Any questions? Now, finally, we will also see some more relationships involving these partial molar properties, and you will see that just as we have relationship between parent various extensive properties, U is equal to P plus PV, H is equal to U plus PV, G is equal to H minus Ts. In a similar manner, you can derive relationship between corresponding partial molar properties. And as a general statement, I would say that there exist relations between Mi bar which are analogous to those between parent extensive properties N. As an example, we will say, for example, we know G is equal to H minus Ts. Now, suppose you want to find out what is the relationship between Gi bar, Hi bar, T and Si bar. T is intensive property, so you do not have to bother. How will you find the relationship? You differentiate it with respect to Ni, keeping temperature, pressure and Nj constant. So, please do that and see what you get. See if you can differentiate it and what you get by differentiation with respect to Ni.
H and S are only the two variables which are dependent on the N.
G, H, S, all of them are dependent on this. T is an intensive property and it is being kept constant actually. So, you must see, we are keeping T constant, that is why you can differentiate it easily. Otherwise, if T was not kept constant, differentiation will become complicated. So, since T is being kept constant, you straight away you can write down the derivatives. What will be the result? You will have immediately differentiation on left hand side, it will be called differentiation of right hand side. It is straightforward expression, no complication at all, because T is constant and each of these partial derivatives is the corresponding partial molar property. dG by dni is equal to Gi bar, dH by dni equal to Hi bar and ds by dni is equal to Si bar, corresponding molar, partial molar enthalpy, partial molar entropy, isn't it? That is the definition of any partial molar property was dm by dni when T, P and J are kept constant. So, if m is equal to H, it becomes Hi bar, if m equal to S, it becomes Si bar, if m equal to G, it becomes Gi bar. So, what do you get as the result from here? This is Gi bar equal to Hi bar minus T into Si bar. So, you get a very simple result, which is quite analogous to the corresponding result for the parent extensive property. Clear? Now, take another property, say H is equal to U plus PV and see what you get. What do you think we will get? Have a look at that equation and see. H equal to U plus PV, that is the definition of enthalpy for a multi-component system. Now, suppose we differentiate this also with respect to Ni, keeping T and P constant. Since P is constant, the P multiplier in V will not create any complication, P is held constant. So, you differentiate, you will get exactly the same result. So, the result would be
del U upon del mg.
HI bar equal to UI bar plus PV VI bar, isn't it? Similarly, you can take free energy. How do you define free energy as? U minus Ts. Again, T is held constant. So, when you differentiate, that multiplier will not cause any complication, and you can easily see that you will get Fi bar equal to Ui bar minus Tsi bar. So, you can see you are getting relationships between partial molar properties which are exactly the analogous to the corresponding relation between parent properties. So, it is a very simplifying fact for us which we can use in predicting the various partial molar properties. We will have to derive some more relationships between chemical potential and others. We will do it in the next class. Okay. Are you comfortable? Is it clear all that we have done? Any questions if you have? If you have any questions on the concepts or on the equations, please ask. It will be slightly more complicated mathematically, so you should be comfortable with this slowly. Okay. So, we will try to solve a few problems also next time.